Okay, so our problem is 542. A cantilever beam having an extended length of 3 meters is subjected to a vertical force of 500 newtons. Assuming that the wall resists this load with linearly varying distributed loads over the 0.15 meter length of the beam portion inside the wall, determine the intensities W1 and W2 for equilibrium. So the length is given, it is 3 meters. The applied load is 0.15 meters. The region of the applied load, distributed load, is given. It is linearly decreasing towards either to the left or to the right hand side. The magnitudes are W1 and W2. Now, first thing that we have to do is we have to draw the free body diagram. Now we have, I will not draw the vertical components, sorry, horizontal components. So we have only vertical components. As you see, we have the triangular region. Then we have a force which is 500 newtons. We say that it is, let's say that that is 500, that's F. So F is 500 newtons. The region that W1 is, or distributed load applied, is denoted as A. It is 0.15 meters, and the length of the beam is 3 meters. Now, first step is to reduce the distributed load. Of course, we choose X as the horizontal coordinate and Y as the vertical coordinate. As a result, resultant of the distributed force is Fw2 and Fw1 here. Now, Fw1 is the area under the distributed load. It's triangular region, so it is W1 multiplied by A divided by 2. Identically, Fw2 is W2 multiplied by A divided by 2. Now, next thing is to write the equilibrium conditions, equilibrium equations. Certainly, some of the equations in x direction has to be equal to 0. We don't have any force component, therefore we don't need to write anything there. Now, second thing is some of the forces in y direction has to be equal to 0. Now, from here, we can easily say that Fw1 minus Fw2 minus F is equal to 0. If we substitute Fw1 and Fw2 into their places, we are going to get W1 minus W2 multiplied by A divided by 2 is equal to F. Now, our third equilibrium condition is sum of the moments with respect to any point is equal to 0. Now, we can take the moment with respect to any point, but in fact, so what we do is simple. So we take the moment with respect to the location where W2 is acting. So with respect to this point. Therefore, the moment generated by F has to be balanced by moment generated by Fw1. Now, the moment generated by F is equal to F length plus 2A divided by 3. So this length is 2A divided by 3. This from here to the location of the resultant force. Okay. And its sign is minus because of the choice of the direction of the positive moment. Okay. And in fact, the distance between the two resultant forces are A divided by 3. As a result, moment generated by the FW1 is FW1 multiplied by A divided by 3, and it has to be equal to 0. Now from here, I can easily say that FW1 is equal to, I can calculate it, 3 divided by A F multiplied by L plus 2A divided by 3. Now from these two equations, I can easily calculate the W1, and I will find this expression. So it is 6 divided by A square multiplied by F, and that's multiplied by L plus 2A divided by 3. Now I know all the values. I know A, it is 0.15. I know F, it's 500. L is 3. And again, A is equal to 0.15. If I substitute all the values, what I'm going to get for W1 is 413.33 kilonewtons. Okay. Now I will do the same thing. Now I can find the W2 because I have the force equilibrium in y direction. So remember that it is W1 minus W2, A divided by 2. Now I know W1, I know F. From here, I can calculate the W2. It is A divided by 2 multiplied by W2. That's equal to W1, A divided by 2 minus F. So I can easily substitute the expression for the W1 here. Then I will have 6A square multiplied by F multiplied by L plus 2A divided by 3, and that's multiplied by A divided by 2 minus F. From here, I can obtain W2 after some algebra. W2 is equal to then 6L divided by A squared plus 4 divided by A, and that's multiplied by F minus F. If I put the values, I know L is 3, A is 0.15, and F is 500. Now I can easily obtain the value for W2. So in order this beam to be in equilibrium, W2 has to be equal to 412.83 kilonewtons.